Welcome back. So today's lesson is chapter 3, Landscapes Fashioned by Water. And so we are going to see this semester that water is a very, very important agent in many, many processes, including on the land, of course, in the ocean, and including in the atmosphere. So water is extremely important to our planet. That's why it's called the blue planet, because of all the water that we learned about. So landscapes, so this will be surface processes that we're going to focus in on in the Earth and Atmosphere course. So all of the internal workings of the Earth are more of a geology course, but in this course we're going to look at the surface processes, sculpting of the land sort of thing. So that's what our chapter 3 is about. And actually, water, running water, is the single most important agent in sculpting of the Earth's land surface we're going to find. So the external processes are what we're going to focus in on. Of course, weathering is a process where you either mechanically or physically, mechanically or chemically will break down material, earth rocky material, into smaller particles. That's weathering. Mass wasting is actually a special type of erosion, so actually picking up and removing these sediments. But this one is usually a downslope motion by the force of gravity, is mass wasting. It's a special type of course, erosion. And they're called external processes because they occur at or near Earth's surface. And so the internal processes, which is focus of the geology course, such as the mountain building, the plate tectonics action, the volcanism and the earthquakes, of course, those are all kind of internal processes that are deriving their energy from Earth's interior. And as we learned in the introductory chapter, that includes radioactivity, all that heat trying to make its way out from the interior of the Earth, and we get the plate motion going on because of that. So that's all kind of internal processes, but we are going to focus on the external processes in here, and of course that is going to be driven by the sun, okay, the action of the sun. Okay, so mass wasting. This is the downslope movement of rock and soil, of course, due to gravity. Sometimes it can just be the simple fact of gravity itself, but a lot of times you get a little water in there, it makes the sediment heavier, and so it sort of triggers that. So there are some controls and triggers of mass wasting that we talk about. And so initially, sediment of various sizes will have a certain stability angle that they can support and that they will be fine with according to gravity. And it is kind of based on sediment size. And so I'm going to pop this little document underneath here. It's called the angle of repose. So it's more or less a stability angle. And of course it is that angle does vary according to sediment size. So something like a very fine sand, as it's showing there, really that dry sand can't support more of an angle than, 35 degrees is about tops that it could do for the very fine sand, where it's stable and wouldn't begin to slough off. Something like a coarse sand, you can get a little bit greater angle of repose. So of course the higher the larger the sediment, the greater that angle will end up being. And definitely if you have some angular pebbles in there, kind of resists the flow there. Angular pebbles, you can get about a 45-degree angle of repose. So that little angle that it makes with the horizontal. So you can pile up your material to a certain angle and it will be stable. But if there's a certain trigger, maybe we add some water to this, or we over steepen our slope, various triggers, okay, can cause the mass wasting that we're going to talk about. But loose, what we call kind of undisturbed, unconsolidated particles, they'll have a stable slope, and we do call that angle of repose, a particular angle that it can support and be fine and stable. Okay. So this mass wasting, that downslope movement of our sediment can be triggered by various things, and so we're talking about, of course, this list here that they're beginning. Water, of course. Water is going to reduce sort of the internal resistance of the material and allow it to flow a little bit better. And it does add some weight to our sediment, and so of course gravity is going to act on that as well. If you over steepen your slope, so cutting into, say, a road cut when they try to widen a highway or something, and you over steepen that stable slope, it can no longer handle it, and things will begin to mass waste and slide down under that influence of gravity. Removal of vegetation, and so vegetation helps to stabilize the sediment by the root systems. Those root systems will hold the soil together. Let me see, I had another little picture in here. So yeah, the root systems and the regoliths, so sort of that unconsolidated material in there, the soil, those roots of the grasses and the trees, various plants will hold the soil together, okay, or hold the sediment together. You remove that, removal of that vegetation, well, then everything is, there's nothing to bind to it. And so that can trigger mass wasting. We see that a lot in California. Maybe you've heard about all those wildfires that they have. They have a very dry season. The winds, the Santa Ana winds will come across and really dry things out, removing all that vegetation from those fires. And then the rainy season comes and it just washes all that soil away, and we end up with tremendous mudslides and various problems like that because of that removal of vegetation. Earthquakes, of course. Anytime you have an earthquake, you're destabilizing the sediment. Yeah, you can get triggers of very large volumes of unconsolidated material mass wasting and sliding down. So various means of triggering the mass wasting, but of course it's all material going down slope under the influence of gravity, and we just call them, you know, several different kind of names that we do call these. One called slump. This is actually something here in Monticello that you see a lot of. If you look off to the sides of your highways, and whenever there's a buildup of land there, you'll see this. You'll see like a little scarp. I don't know how well you're seeing that on the screen there, but a little scarp of a slump. Okay, we get a lot of this here in Monticello. Another one, rock slides. Maybe if you go to northern part of Arkansas where we get more mountainous terrain, certainly in Colorado, the Rocky Mountains, you'll see all these signs trying to warn you about a rock slide that can happen, and you see how it just tumbles down, all that talus and debris tumbles down across the highways, and it just blocks out the highways and hopefully doesn't hit any of the motor vehicles there. Debris flow, this one is like a slurry. Again, we see that out in California a lot. A slurry of mud and material and debris, and it will just really coat and cover. It can engulf homes and vehicles, go across the road like it's showing there as well. So yeah, we see that a lot out there in California. An earth flow. Now an earth flow is very, very slow, to the point that sometimes they call it a creep. Let's see if I can find my little handout. Here it is, earth flow, they call that. very, very slow for this. So creep is what they call that. You almost don't notice it because it's very, very slow, but the effects of it on a fence, let's say, it will, this little image here has the fence all going out of alignment. Well, they didn't build the fence incorrectly. Over time, the land has moved and shifted your fence there, so it's no longer in alignment. Here's another one where perhaps you see, say, a tree that has a curved trunk. A tree is going to grow straight up, towards the sun. It's not going to curve like that. So this indicates that you have had a creep or an earth flow to happen when you see curving of a tree trunk. Another telltale sign of earth flow is telephone poles that are like leaning, right? So here we have some tilted telephone poles in there. Of course, your fences. I think they had some tilted gravestones and different things in this little image here. So lots of ways you can detect the earth flow, even though maybe you're not visualizing it as it's happening, but over time you can see the effects definitely of this. So these are all examples of mass wasting, we call that, which is a special type of erosion. Everything's going down slope, downhill with the influence of gravity. Oh, and here is an image in Monticello. The student, Robert Hargis, got this several years back, so he's the credit for the image. But yeah, lots of places here in Monticello you drive and you will see the slump. Remember, a slump is what we really see here in Monticello. That type of mass wasting there. So that was I'm not sure if that's in your PowerPoints or not, but that was an image a student had taken. So the importance of water. We're calling it here the water cycle, but it's also known as the hydrologic cycle. But this is that continuous motion or movement of water from the ocean to the atmosphere, back to the land, and makes its way back to the ocean. So pretty much what we would call a cycle, even though it can take little inner missions in there, but it is like a cycle, they call it, and hydrologic cycle. So for that term there, hydrologic cycle. Hydro meaning water, okay. So yes, some terms in here. You have one of these in your book, right? They may have one in the PowerPoint as well, and it gets a little busy. This one's pretty simplified, so we can see some of the terminology that they're going to talk about in the PowerPoint. But really, that energy source that is driving the hydrologic cycle, once again, is the sun. Very important for these external processes, including the hydrologic cycle. So the hydrologic cycle is an excellent example of the interrelationships of the four spheres we talked about in the introductory chapter. The Earth's four spheres. Of course, the biosphere, that's us. But we've got the hydrosphere, the geosphere, and the atmosphere. This one has got all of those, okay? So we've got, of course, the sun driving this. So evaporation from the ocean, okay, and streams and lakes, of course, but evaporation, taking a liquid and going to vapor. So that gets it up into the atmosphere, okay? Water vapor, okay, going up into the atmosphere. Of course, and we'll learn a little later in the course how condensation happens to create the clouds. So condensation, we're taking water vapor and going back to a liquid, little tiny liquid droplets or ice in our clouds. So you get some condensation happening, and then eventually you reach your saturation point and you're going to get some precipitation from your clouds. That precipitation can be in the form, many forms, snow, hail, of course rain, coming back to the land, right? So we've got it back to the land there. Now, once it gets to the land, it can do a few things. It can infiltrate into the soil. There's pore space in the soil that it could infiltrate into. Or if your surface is kind of impermeable, maybe asphalt, something like that, or a clay that really doesn't want to absorb very well, it will run off, okay? And it can run off, so it can infiltrate, it can run off. You can get transpiration. That is from the leaves of trees, grass, and that such. So you're essentially getting evaporation back to the atmosphere through transpiration of plants. So there's your biosphere getting in on it. But that material, that water, is going to make its way ultimately back to the ocean. So even the groundwater will move. It's slower, but it will move and make its way back to the ocean ultimately. Of course, our streams, it could go through the streams as well, but ultimately back to the ocean. And so we would say we completed the cycle, the water cycle. So the hydrologic cycle is the term we use in the earth sciences. So there's some of that terminology that it's going to talk about there, but basically these are the processes involved in that movement of water from the ocean, right? Evaporation happens from the ocean. We get condensation in the atmosphere with the clouds. Some form of precipitation occurs, bringing it back down to the land, right? And you can get infiltration, you can get runoff, you can get transpiration from your plants, right? So all of those processes are part of that motion of water from the ocean to the atmosphere, back to the land, and ultimately back to the ocean. And so you'll see that here on this diagram in your PowerPoint. Now you're not going to have to remember the amounts, so they're talking about cubic kilometers. You won't have to remember any of those numbers, but the processes, we want you to remember those processes in the hydrologic cycle. Okay. Distribution of Earth's water. Okay. It's not equally distributed across the planet. And so, let's take a look at this. I think we learned this in the introductory chapter, that the majority of all the water on the planet is in the ocean. So 97% of all the water, if we were talking about 100%, 97% is in the ocean. And that is salty water. We will talk more about the ocean separately, but that's all salty water. That's not water that we as humans can consume. So that gives us roughly here about 3%. That's what we would call fresh water. Okay. Of that 3% remaining, that's fresh water that potentially humans could use. Okay. 2/3 of that, about 2/3 of that, is tied up in the glaciers. So it's frozen, solid. We can't use that, okay, of the fresh water. So here we have the glaciers here. So that leaves us about, a 1/3 here going on of 1%. And of 1%, okay, of that remaining kind of fresh water happening for us, only about 0.6%, so only about 1/3 of that can be used by humans. So it's in the form of groundwater. So groundwater is the largest reservoir of fresh water available for human consumption. The remaining of that 0.3%, okay, up in the atmosphere, of course, we've got a little water vapor up in the atmosphere. Very important that we've got it there. If we think of our streams and channels, our rivers and our lakes, it's really only 1/3%. And you think of the mighty Mississippi, all the water there, the Amazon River, and all the water there, that's only 1/3 of 1%. of all the water on the planet. So the majority of water that is usable by humans is in the form of groundwater, and we will be touching a little more on the groundwater at the end of this chapter here. So I do want to kind of look at a map here. I don't know how well it'll show up, but it's a climate map, a world map, and it's color-coded, which is very interesting. So right along here, there, of course, is the equator, cutting it in half, so 0-degree latitude, equator. And the color coding on here, the yellows and the browns are sort of our desert and steppe regions, and a steppe is sort of a semi-arid region. So if we look about 30 degrees north and south of the equator, so a strip right about here, we look across there, and again, 30 degrees south, and you look at a strip right along there. Those are where the great major deserts of the earth are located. This is a place where you have a deficit of water, our desert regions, and it straddles the equator about 30 degrees north and 30 degrees south latitude. And we'll learn later why we see that. But in along here, I would say about 10 degrees north and south of the equator, all of those pinks and kind of salmon colors on the color coded on here, those are our tropics, where you have an excess of water in those regions, the tropics regions, very wet regions, climates there. And we'll find out what's going on atmospherically to cause that a little later in the semester. But for now, we can see that across the planet, the distribution of water is not equal. Okay, some places have a lot of it, some places don't have enough of it. So we can actually think of water as a precious resource, almost like it's a non-renewable resource for us, because that fresh water is really coming from our groundwater, and that becomes really a precious resource for us. So yeah, we'll see how that distribution is not equal across the planet. Okay, so we want to look at, again, running water, the sculpting of the land by running water. Again, running water is the single most important agent in sculpting of the land surface. And so running water flowing through our streams, we'll be taking a look at our stream, the work of streams. Of course, streams are going to erode, right? They're going to remove sediment. They're going to transport that sediment, so transportation of the sediment. And eventually, the velocity of the stream will slow down and it will deposit that sediment. So streams do three things. They erode, they transport, and they deposit sediment. So the work of streams we'll be looking at. And of course, it's doing this all along the stream, but maybe some of those processes are being emphasized over others, okay? But keep that in mind. All streams will erode, transport, and deposit material. So stream flow is the ability of a stream to erode and transport its materials, and of course that is determined by the velocity, that stream flow, how fast the stream is moving, okay? And we do have some factors that do determine the velocity, so the speed, how fast the stream is moving, okay, that velocity. The first one here that they talk about is the gradient or the slope, okay, of your stream. And so this is basically a little calculation you can do, but basically it is the difference in the elevation, okay, so how high is your stream beginning to how low does it go over a particular distance. So it's sort of the change in elevation over distance. So I've got a little image here that can help us to see that. but this is called stream gradient or slope, they call that. I can find a piece of chalk for us. Right, but you can see here on the little diagram that the difference in elevation. So here we are at, say, the headwaters of where our river or stream begins, right? It's kind of up in a higher elevation, and then it's going to go down to a lower elevation, right? As we go towards the mouth of the stream. Down here would be the mouth of the stream. And so that difference in elevation, so pretty much kind of a change in elevation. So my little triangle stands for the change. So G for gradient. But your change in elevation, okay, so what's the difference in elevation over the horizontal distance? So divided by the distance. So this would be your slope or your gradient of your stream. Okay. And so, yeah, you can do calculations on that. And of course, all water, surface water, groundwater, is going to move downhill, right, by the force of gravity. That's a fact. So remember that. It's all going to move downhill under the influence of gravity. But how fast is it going to be doing that? What's our gradient? What's our slope? And so let's say, and I've got some numbers here, let's say we had a change here. We went from 0 feet, let's say, up to 5,000 feet. So we went, let me write that again. Our change in elevation was basically going from 5,000 feet down to 0, let's say. And it doesn't always have to be 0. But just for making ease of this, we'll call it 0. And let's say it went over a distance of 1,000 miles. We'll put that in miles. You could certainly, have that in a metric unit as well. But feet per miles, that would kind of be what the unit would be for gradient. So many feet per mile is sort of the unit you would see. So basically, yeah, that difference is 5,000, right? So 5,000 minus 5,000, or 0, is 5,000. And so if you were to kind of do your division, right, all those zeros will cancel, to where you'd end up with 5 feet per mile as your gradient, okay, your gradient or your slope. And certainly you could get steeper gradients. You get up in the mountainous terrain, you're going to get probably a much higher gradient. You go down towards the lower part here, maybe towards the Big Easy, and maybe you're only getting a few inches per mile of a gradient. It's a little flatter terrain. And so the stream gradient, okay, what that change in elevation over a particular unit of distance is going to affect the speed of your stream flow. And so, of course, a steeper gradient, a higher gradient, is going to give you a faster velocity. Okay, so the gradient or the slope is a factor that will determine the velocity as one of your factors that can determine the velocity. And we'll want to make sure that you can do a gradient calculation like that. So I would, of course, give you, your elevations. You just subtract them, so that's that difference or that change in elevation. And of course, your distance would be given as well. So make sure you can do a little calculation on gradient for the exam. Okay, another thing that can affect your stream flow is the channel characteristics, including shape, size, and roughness. Now, a variety of shapes you can get with your channels. So let's say we had, maybe a really kind of a very wide channel, but not too deep sort of thing. You're going to get a lot of friction. That water is going to be in contact with that very wide channel bottom and the sides of the channel. that's going to act to slow your velocity down. A shape that would give you a very high velocity would be sort of a semicircular shape. For a semicircular shape, you're getting the majority of the water towards the center, and so that flow is unhindered. Very little friction out to the sides when you have a circular or semicircular kind of a channel. And that is why our pipes are in that circular kind of shape. The water is going to zip right on through with very little friction with the sides and the bottom of your channel. So yeah, I'd say a semicircular shape would be your best shape size for a fast velocity. The size, of course, the larger the size your channel, the more material going through that can kind of get pushed behind by gravity, and that'll cause it to be a faster velocity. Roughness, so you want smooth channel sides, things that can slow your velocity down. The roughness they're talking about, you can get, boulders, lots of rocks and things in your stream channels. Sometimes over fallen trees, tree limbs get in there. Sometimes people just throw their junk into the streams, unfortunately. That can slow down that stream flow, okay, that resistance, sort of friction that's happening. So you really want smooth sides, large channel, and that semicircular shape. That's all going to give you some really high velocity for your stream flows. So of course, channel characteristics can make a difference to offer that least kind of resistance to flow in there. Another thing, something called discharge, right? So the discharge, the volume of water that moves past a given point, okay, in a certain amount of time. So again, how many little, what we call tributaries, are joining your main channel? So there'll be all these little ancillary streams that can connect to your main channel. So the more kind of volume you get, that's going to, again, push that material a little faster. So the volume of water moving past a certain point is known as the discharge of the stream. So, of course, a larger discharge is going to give you a larger velocity. So this can change along the stream. It doesn't stay the same all the way down the stream. So we do kind of talk about the headwaters and then the mouth of the stream. So this is coming from your book, from chapter 3, Zones of the River. If they're in the head zone, right? Again, different processes are emphasized as we go through. Clear down to the mouth, more the zone of deposition. Up here, more the zone of erosion. So different things kind of going along, and here they're saying sort of the zone of transportation, the movement of things. But yeah, things can change along your stream, so they don't stay the same all the way down. Okay, so changes along the stream that can happen. Kind of a profile, a cross-sectional view of a stream is called a profile. And you can look at it viewed from the headwaters, and that little image was showing the headwaters, which is the source of your stream, towards the mouth of the stream. That's where it's eventually going to flow into a larger body of water. Ultimate base level would be the ocean, okay? The mouth of the stream, we would call that. That can change. All of those things can kind of change as you go. So the profile is a smooth curve, and of course your gradient is going to decrease downstream. Let's just take, for example, the Mississippi River. It begins way up there in Minnesota. This is thousands of miles here of a stream, a river basically, but it begins way up there, higher elevation. Okay, higher elevation, and then as you get down and think about the Mississippi River, the mouth of the Mississippi River down there in the Big Easy, New Orleans area, not such a great elevation any longer. So your gradient will decrease as you go downstream, okay? But things that do increase as you go downstream it might be counterintuitive to think that velocity is actually going to increase downstream. And if you think about it, and you think about how all those tributaries coming in and feeding into the main channel, your channel size actually gets larger as you go downstream. So more volume of water is downstream. So of course that is going to increase your velocity downstream. Of course your discharge, your volume of water is going to increase downstream. And of course channel size, all of those ancillary little streams adding to the main channel, right, that's going to make your channel size larger as you go downstream. Okay, even though gradient is decreasing downstream. So here's an image, right? So here's where the headwaters is, where the source, higher gradient, right? Higher elevation, the steeper gradient along there. But look at all the tributaries, right? These ancillary streams coming in and feeding into the main channel, right? You see sort of the meandering motion. The channel size is getting larger. The amount, the volume of water is increasing, so discharge is increasing, and those two factors together will increase your velocity downstream at the mouth. And there's the ocean where it is feeding into, ultimately, the ultimate base level is the ocean where these will feed into. And you can also note right here, notice how coming from the main channel, these little branches are going away from the main channel. Those are called distributaries. We got the tributaries coming in, and then the distributaries, like it's distributing, distributaries coming away from it. And again, erosion is kind of a dominant process at the headwaters, transportation zone, and then a deposition zone. Velocity, everything, we begin to deposit the sediment, kind of dominates the processes at the mouth of the stream. So this is a nice profile, kind of looking at that sort of in a longitudinal kind of look to it. I mentioned base level a couple of times. So base level is the lowest point to which a stream can erode. How far down it can cut and erode down, to what level. That's a base level. There's two kind of general types of base levels. I mentioned the ultimate base level being the ocean or sea level. Okay. Or it can be a local or a temporary one. Sometimes we can get erosional resistant rock, and that can be considered a local or a temporary kind of a base level. We can put up artificial blocks to our streams, dams. We put up dams, and that can be kind of a temporary change in our base level, how far our streams can erode down to. So we do put up dams, and you'll see a little image with that. One without a dam and one with a dam. But changing conditions causes the readjustment of the stream activities. And so if we were to raise the base level, okay, you raise your base level, that's going to cause material to deposit. So it causes deposition. If we lowered our base level, let's say sea level decreased, now the streams can downcut and erode to a lower level. So lowering a base level causes erosion. It allows you to erode even lower on the land surface and sculpting of the land. So changing, our base level can change whether we're having deposition happening or whether we're having erosion happening in there. Okay, and so here's that picture of where adjustment of a base level according to what kind of changes of conditions. So here's kind of an unimpeded stream coming along, and it's adjusted down cutting or erosion according to what the ultimate sea level is at the time. And that kind of dictates how low the stream can erode, okay, down to. So that's kind of that image there. This one down here, well, we put up a dam, Okay, so sort of a temporary or a local adjustment of the base level, which the ultimate base level was the ocean. But we put up a dam here. And so here you go along. Here's where the original base or down cutting motion would have been from the original profile. But because we put up a dam, that impeded our stream and it caused deposition to happen, okay? So along here, you're getting the new stream is becoming formed here to deposition because the dam is slowing the flow, and then all that material that it was carrying is going to drop out because the velocity slowed down. And so it changed kind of the level to which that stream could erode. It's depositing now towards here. And so every now and then with a dam, you're going to have to go in and dredge it out because, yeah, you're going to start to kind of get all that deposition happening because of the dam. So they can be good, but, you know, it's a temporary kind of a thing here. You're going to have to continuously kind of be digging and dredging the dam area out. Okay, so you can get adjustments of a base level by changing your ultimate base level. Waterfall is an example of a local base level. So we had sort of erosional resistant rock here, right? It's not easily eroded, and it created sort of a kind of new base level and then the waterfall occurs from there. A little example of a local base level. Okay, so here we're looking at the work of a stream. And so we've already mentioned that streams do three things, okay? They're going to erode. And so kind of the first thing they're talking about here is going to be erosion of the land, sculpting of the land here. And it's going to transport that material along, down a ways, and then deposition will happen. As stream velocity slows, you're going to get material dropping out and depositing. So, three things. It's going to erode, transport, and deposit. Just keep that in mind all along here. So, the work of streams, they're going to first start talking about stream erosion. Okay, kind of lifting loosely consolidated particles, sediment material. Couple ways it does that. One is by abrasion, so scraping kind of just past it. You think of maybe some sandpaper and abrasion, okay, is one way. And dissolution. So that term dissolution means that it dissolves material. Okay, water is a great dissolving medium for many, many substances, but it can dissolve some of that material and carry it on down the line. So it can actually abrade it, or it can dissolve material. Okay. Of course, a stronger current you have, so the higher the velocity you have, you're able to lift more particles and larger particle sizes. Okay. So more sediment and larger particle sizes. The greater your current, the stronger your velocity. So being able to lift, okay, that material or dissolve that material, that's erosion. Okay, transporting of the sediments. So most streams, honestly, are going to carry their largest part of their load, of course, in suspension, kind of lifting it. But we have several types of load that we talk about. So transported material, of course, is called the stream's load. It's dissolved load. So the material that gets dissolved in the water can get transported. It's called dissolved load. Suspended load is it's actually supporting it, buoyantly supporting and suspending that load in the water, right? Bed load is like pushing or somersaulting that material across the bottom. And these can be some rather large, even maybe boulder sizes, but you'd have to have a really high velocity to move a very large boulder. And it can happen. Say you had a large flood, right? So maybe during a huge flood, scoot that material along the channel bottom, and it'll go a few feet maybe, and then it'll sit there for a long time. And then it'll maybe go a little further. But something like a bed load, it's getting moved along the bottom of the channel. But really, the majority, the largest amount of material gets moved along or transported as a suspended load, okay? Streams carry most of their material as suspension, okay? Suspended load, okay? We have a couple of terms in here. One's called capacity, the other one's called competence. So 2 C words for you for your definitions. But capacity is the maximum load a stream can transport. So the maximum amount of material is the capacity. Maximum amount of material that the stream can transport is its capacity. Okay, that's amount of material. Competence, on the other hand, is the particle size. So how large a particle can the stream carry, okay? So maximum particle size a stream can transport. And of course that is going to be determined by the velocity of the stream. The greater the velocity, so the faster the speed of your current, the greater the particle size that can be moved, okay, transported. So that is very dependent on the velocity of the stream. And that does make streams very good at sorting the material. So you will find, we'll look at some either sandbars or gravel bars, but very well sorted material, meaning that the particle sizes are all the same. You either get, very fine-grained sand, coarse-grained sands, gravel-sized sediments, so very well sorted. And the reason it's so well sorted is because of the velocity of the stream. And that particular velocity can only lift a certain size particle. So when the velocity drops, that material will drop out, and it'll be very, very well sorted. So streams do a really good job of sorting material. Okay, but capacity is the maximum amount of material. Competence is the maximum size of the particle that the stream can carry. So those are your 2 vocabulary words there, the C words there, capacity and competence. Okay. So yeah, caused by a decrease in velocity. So deposition of sediment. So when that velocity dies down, it can no longer support all that suspended load, right? And it's going to begin its deposition phase, right? So a decrease in velocity, your competence is reduced. So the maximum size of particle that it can suspend is reduced when velocity slows down. And those materials are going to start to drop out. So deposit, or we call it deposition. Sediments are going to begin to drop out. And so as I mentioned before, streams, the stream sediments, they are generally very well sorted. You're either going to see kind of all the same sand-sized particles or all the same gravel-sized particles because it's due to the velocity. Things are going to drop out according to velocity. Of course, your largest particles are going to drop out as that velocity begins to slow. Maybe your sandy material can, still be transported, but eventually it'll slow down enough that the sandy material will drop out, and then maybe the silt or the clay-sized particles a little further down because those, can still be suspended. So very well sorted, the work of our streams. We do call the stream sediments alluvium. If you remember, let's see if I can grab my little Arkansas map, our geographic provinces. And so if you recall from looking at that, I'll pop this under here quite frequently. So these were our basic provinces, and according to what is going on with the bedrock. Notice over here in the eastern part of the state, okay, of Arkansas, Mississippi River alluvial plain. So alluvium, that is sediment that has been brought by a river, okay, alluvial, alluvium. And so of course the Mississippi River, notice the meandering motion of our river that just naturally will do that. That's sort of, we're in a floodplain over here. This is a floodplain. Of course, Drew County here, Monticello is not in this floodplain, but of course eastern part of Drew County is in there. And then of course Dumas, McGee, all those locations off over there are within the Mississippi River alluvial floodplain out in there and along there. So of course that's where that term kind of is coming from, the alluvium. That's sediment, okay? And so, yeah, and well, I'm gonna mention that again here. You've got places out there, the farmland out here in eastern Arkansas, really good sediment out there that's coming from the alluvium, being brought by the Mississippi River, right? So really good farmland out there here in eastern Arkansas. But this is best described as an alluvial floodplain. Okay, so this is actually the floodplain region of the Mississippi River. So talking about Arkansas there, so you might tune in. But that farmland in the eastern part of Arkansas is a deposit that's best known as, best described as an alluvial floodplain out in there. Okay, in Arkansas stuff, so we pay attention when we talk about Arkansas, right? But deposition of a stream, right? So that term there, alluvium, kind of where that term come from on our Arkansas map there. Okay, and so as our stream or river kind of enters a still body of water, right, velocity is going to drop off. It's almost like it's slamming up against the wall there, and it will deposit, right? It's going to deposit that sediment load, and then what we call here, a few things can happen here. As it enters ultimately the ocean is what we think of, a sudden decrease in velocity, and it creates what we call a delta. Okay, and so that term delta, particularly in this region, has been misnamed, kind of entrenched in our culture here in Arkansas. So the true delta is way down there in the foot of Louisiana, where that enters the Gulf, okay, of Mexico. That's the true, what we call delta. But this region has been called the delta, and you know, are they going to go and change all of their, you know, signs about the delta? But the true delta, okay, here in the United States, the Mississippi Delta is at the foot, okay, here of Louisiana, where the Mississippi River enters the Gulf of Mexico. That's the true delta. And so, yeah, I'm not sure where all that came from, but it's so entrenched in our culture that, you know, it'd be hard to move people away from thinking that this area is the delta, but it is not. That's not true. So it's where it enters the ocean, right? You've got your delta, your true delta. Something else that can happen, deposition kind of work that happens, is what we call a levee. Natural levees can build up, and this can happen from successive floods over, of course, many years here, but it forms parallel on either side of the stream channel. So as you get a flood, that water is going to go up over the channel sides of your stream, and that will leave a deposition, a little mound of material on just paralleling your stream. Okay, and so that's called a natural levee. Of course, we build levees to try to control our streams, keep them where we want them, sort of thing, but that's a natural kind of levee that forms on either kind of side, and those are depositional structures that occur from streams. So we talked a little bit about erosional things, but this is deposition structures. So a delta and a levee. So notice that the meandering kind of motion, the sinuous, snake-like sinuous motion, that's a natural movement of our streams. They tend to meander like this. So of course we've got a area that is going to be eroding out, right? Kind of eroding out. We call that the floodplain. Okay, that's the region that the extent of the floodwaters would go, okay, when they overflow the banks. But we can get some other things that kind of happen in there. When some of this water overflows the natural levee, right, builds up that sediment on either side, sometimes that water cannot get back into the main channel. And so we end up getting something called a Yazoo tributary. And it just sort of does its own little thing, meanders its way along for many, many, many miles until maybe it can breach the levee and get back to the main channel. But the Yazoo River, if anyone's familiar, kind of in the area, there is a river called the Yazoo River, but they're all called a Yazoo tributary, okay, that it just goes parallel kind of to the main channel for a lot of miles. The Yazoo River, 190 miles, it parallels the Mississippi River. You can get things like a back swamp, some little puddles, pools of water that can't get back in to the main channel. And so you can get a little back swamp, they call that. But yeah, so every time your river channel floods, right, you can get a buildup of deposition on either side, and we call those natural levees. Again, depositional features here. Floodplain kind of deposits. So the back swamps that we talked about, that material, that water that just can't get back into the main stream, and the Yazoo tributaries, they just go miles and miles kind of parallel the main channel, right? And so the Yazoo River, kind of Greensburg area, the Vicksburg, kind of Louisiana area, where I don't know if any of you have seen the Yazoo River. That one, yeah, that's kind of what happened. It kind of got cut off from the main channel, and it sort of parallels the Mississippi River. Okay, the most common landforms on Earth's surface are what we call these stream valleys, okay? And there's a couple types of stream valleys. Ones we call narrow valleys, and this is where erosion is really down cutting towards the base level. Features often include rapids, so very choppy, turbulent water, and lots of waterfalls as well. But erosion is very, very dominant in a narrow, sort of V-shaped type of a stream valley, we would call it. But erosion is very, very dominant in this one. So something like rapids would be seen in a V-shaped valley. Okay? And erosion, again, is very, very dominant in that one. Versus wide stream valleys, so you're already very near your base level, so the stream is near the base level. So the downward erosion is not very dominant. It's not down cutting. Erosion is still occurring, but it's more of a side to side type of combination of erosion and deposition. So these are very wide, as it says, a wide valley. Think of a floodplain. Okay, think of the floodplain as a wide stream valley. that you would see in a wide stream valley. Let's see, I think I had a picture of the Mississippi kind of barriers on each side, what the walls of that wide stream valley is. Of course, Mississippi going down and along there. But actually here in here in Arkansas, oh, you probably can't see that too well, but a little town not far from Monticello here called Collins. Okay, so Collins, Arkansas, it's kind of on that road as you're trying to go towards Dermot, is the wall of the eastern side, or the western side of that Mississippi floodplain. Okay, Collins, I kind of have an arrow here for Collins. You probably can't see that word there. So that's the beginning, right? You got Dermot and other places, Lake Village over here, if you've ever been to Lake Village. We'll talk about that again in a sec. And it goes across, here's your Mississippi River doing its thing, meandering, comes all the way over here on the other side to Greenwood, Mississippi. So Greenwood, Mississippi is the other wall of that wide stream valley. Okay, so that floodplain. All along there, straddling across the Mississippi River, all that distance. That is including the floodplain. Okay, so yeah, kind of as you go down the hill just east of Collins there on your way to Dermot, right? That's the valley wall of the Mississippi River floodplain. Okay, so again, oh, where'd my little, at least over on the Arkansas side, of course, of things. Right, so not far from Monticello as you're going off this way. Of course, Monticello isn't in the floodplain, but just kind of to the east of that, that's on one side. That's sort of the one wall of the Mississippi River floodplain. Of course, over here in Mississippi, where Greenwood is the other wall of the floodplain. Okay, so just a little Google Earth image I had there. So again, Arkansas stuff, so we want to make a note of that. Just east of Collins on the road to Dermot, that's the valley wall of the Mississippi River floodplain. That's characteristic of a wide stream valley. They have a couple other terminology here as well that you would see in a floodplain. In our floodplains, you can have erosional floodplains and depositional floodplains. Okay, so they're going to talk about both of these, some features that we'll see. So, of course, meanders, as we were seeing, Mississippi River meanders. So these long, sinuous kind of paths. This is a natural tendency to flow in sort of a curved, sinuous pattern, side to side, like that. Those are known as meanders, okay? The stream's natural tendency to flow in that curved, sinuous pattern. Things we call cut banks and point bars, okay? I'm trying to see if I had, yeah. I think they'll have a picture for us in your PowerPoint, but I had another one as well there. Cut banks and point bars. So cut banks are erosional, okay, where the velocity of the stream is higher and it's going to cut into the sediment. So a cut bank, erosion's happening. And a point bar is where, oh, the velocity dropped off a bit and now we're depositing some material. So you can get some point bars, and really depending on, you know, the velocity and how large a material it was able to suspend for a while, as it deposits it out, you can get a sandbar, maybe you can get a gravel bar, again, whatever was going on with the competence of your stream flow, how large a particle it could have supported. That material drops out at a point bar. So these little gravel bars or something like that. Other terms that we'll look at in the picture, cutoffs. So there's enough, if you get a buildup of enough sediment, it could actually cut off one of the little meanders. So a cutoff, sediment builds up enough that the stream is going to continue going straight, and you've got this little meander loop that kind of gets cut off, they call that. And then if it creates sort of a horseshoe kind of shape, we call it an oxbow lake. We actually do have an oxbow lake here in Arkansas, kind of a famous oxbow lake. Let's see. Yeah, there's not a bad picture. I kind of like my picture better that I've got. So I might pop this one in here. Okay. So it's got a lot of these terms in here that the PowerPoint was just talking about here. So here we have a very wide floodplain, right? Kind of have your levees built up on either side, and the stream is doing its meandering along there, the meander belt they call that. But yeah, along on the sort of outer part of the bend of a meander, you're getting erosion happening. They call that a cut bank. You can see where it's cutting into the land, so eroding the land. They call that a cut bank. On the inner side of the meander, okay, the velocity is slower, and so you'll get deposition happening in here, right? So it's going to create a cut bank on the outward bend and create deposition on the inward part of the meander, and that's called a point bar. Some of those terms we just were looking at. Of course, here's your natural kind of levees on either side, the alluvium, that sediment being brought by the rivers. Here's the Yazoo stream going along there, a little back swamp there. Some of those previous terms we looked at. But here's a cutoff. So here we had enough deposition to happen, right, that the river decided, it's easier to go straight through here rather than go around the loop, okay? And so it pretty much is getting pinched off or cut off in that region. Here, it's been really cut off and left behind almost like a scar of a meander, and it's called an oxbow lake. We have an oxbow lake here in Arkansas in the Lake Chico area, the Lake Village area. Kind of why they call it an oxbow is because of the shape. Got something here for your notes there. Lake Chico as an oxbow lake. And so here along here is kind of the Google Earth picture. The Mississippi River was going along, right? And you can see a little point bar there, a buildup of material. This was part of a meander of the Mississippi River, but it got cut off, right? It got cut off and left behind, and they call it an oxbow lake, okay? You could actually go and visit the Lake Chico State Park. It's a very famous oxbow lake, right? So we've got the state park for Lake Chico State Park. But what's going on, they're calling that kind of shape, it stems from what you would put on oxen, right? An oxbow, they call that. Sort of that little pattern that they're looking at. Kind of how it got its name, the terminology for an oxbow lake. But definitely that is something here in Arkansas. If I can find our little map again, keep misplacing that. There it is, right down there, Lake Village, coming off of the Mississippi River. The little oxbow lake that we have here in Arkansas. So that is a very good example of an oxbow lake, Lake Chico. Get back under there for your spelling of Lake Chico. Great example here in Arkansas of an oxbow lake. Excuse me. Okay, and so we do have some rivers that will kind of change their course. I don't know, let me see if I have a picture of this. For example, the Arkansas River once flowed in a channel that's now called the Bayou Bartholomew. So they will change their course, right? They're going to try to find the path of least kind of resistance. So here's the Arkansas River, right? It actually used to take this path, okay? And this is Bayou Bartholomew, if any of you are familiar with that bayou. But it actually used to take this path, Arkansas River once did, but it found it easier, less resistant path, and so now it follows this path and makes its way to the Mississippi River and feeds in. It's a tributary of the Mississippi River. But yeah, the Arkansas River actually used to flow along what is now we call Bayou Bartholomew, a very slow moving bayou, they call that. So yes, these over time, yes, these rivers can change course, right? Because of the meanders, and they're finding the path of least resistance. And sometimes, you know, you can get those cutoffs that can happen, and then it'll end up taking a different path. And here's a meander, a loop of the Colorado River. And just the meandering nature of our rivers. That's just a natural tendency for them to go in that curved kind of flow. Okay, floods and flood control. So floods are the most common and destructive geologic hazards. In fact, it causes the most deaths of all atmospheric, let's say, weather kind of related hazards. Floods are the most destructive and cause the most deaths, we'll find. You know, more than hurricanes, more than tornadoes, lightning strikes, this kind of thing. Flooding takes more lives. But the causes of flooding, of course, that's naturally occurring, resulting from natural occurrence, and human-induced factors. So we can play a role by, you know, putting up dams and different things. We can change kind of the course of that natural flow of things. So some of our causes, of course, heavy rains, getting rains for a great intensity, you know, long-term kind of thing. Yes, that's going to cause a problem. Rapid snow melt. So here with the Mississippi River, it starts way up in Minnesota. They get a lot of snow up there. That snow will melt eventually. All that water's making its way to the Mississippi River, and that volume of water is going to come down our way eventually. So snow melt, adding to the volume of water. Dam failure. So yeah, we try to control our rivers by putting up dams, but your dam can break, your levees can break, right? The topography, so that term topography, you'll hear a lot about that term, especially if you're in the lab this semester. Topography, sort of the shape of the land, will have a lot to do with your flooding, your potential for flooding. Your surface conditions, so you know, what material is your soil? Do you have a clay soil? Do you have a very porous soil that drains well? You know, a lot of these surface kind of conditions. So a lot of asphalt or, you know, concrete, that's not very porous material. So we do make efforts to try to control the floods, putting up artificial levees. There was actually a great flood, the 1927 flood. Let me see if I can find my old little thing for that. Where did it go? Here it is. Yes, the Great Flood of 1927, where the levees broke. Okay, I don't know how well you can see that, but the date is 1927. This was a devastating flood for like a 7-state area. And so, yeah, the little plaque there says, after months of rainfall, a swollen Mississippi River broke the levee at Mound Landing, some 2.5 miles west, on April 21st, 1927. The floodwaters caused widespread destruction and loss of life in 7 states. The breadth of the disaster focused attention on the Delta and helped initiate a national flood control program. So this really made some major economic, political, and cultural changes to Arkansas, Mississippi, Louisiana. You see a gentleman here, he's on a little bit of a railroad, a piece of the railroad there, and you can just see water has covered everything, destroyed the homes of so many people. So culturally, it really did influence a lot of the music. We call it the Delta Blues, kind of stemmed from the Great Flood of 1927. There's lots of music from this. When the Levee Breaks by Kansas Joe McCoy and Memphis Minnie. That's my favorite recording, talking about when the levee breaks. But this prompted a mass migration of Black Americans, African Americans, northward. They lost everything and they had to move. They couldn't rebuild and they had to move and migrate. So this really politically, culturally, and economically really changed this flood, this 1927 flood of the Mississippi River. Really changed the climate here, for sure. So 1927, make sure you got your date there. When the levees did break. So yeah, that did prompt the Army Corps of Engineers to go in and, really build a national levee system. We're trying to control the Mississippi River, keep it in its banks, kind of thing. So really doing a lot of artificial levees, flood control dams, trying to tame that river and keep it in its banks. Channelization as well. Again, trying to dredge out the channels to make it go the path we want it to go. It naturally wants to meander, but a lot of times we need it to be where we need it to be for shipping and transportation of our materials and our goods. We kind of need to control that. So channelization is something we try as well. But yeah, sound floodplain management is what they try to do to contain it as best they can. It's a never-ending job, though. Trying to tame the mighty Mississippi. Okay, drainage basins and patterns. And so, drainage networks. I do think I had a picture of the Mississippi drainage basin. It's very large. Here it is. And I think your book, or there might be a PowerPoint of it, but this is really color-coded pops kind of thing here. So you have several rivers, Missouri Red River Basin, the Arkansas White River Basin, Lower Mississippi River Basin, Ohio. All of those feed into the very large Mississippi River drainage basin. They all go into the Mississippi River. So this is huge. This is a major drainage basin here in the United States, right? Oops. That is very large there. Okay, so that's the land area that contributes to the stream. Okay, all of that water going into the stream. In this case, it's the Mississippi River is the ultimate one. That's called a drainage basin. An imaginary line separating one basin from another basin. As we were seeing, we had several different basins in there, all ultimately going to the Mississippi. But yeah, you'll have what you call divides. So it separates one basin from another, and it's known as a divide. We actually have some natural divides here in Arkansas, and even closer to home, kind of near Monticello area. But it's a divide. It's an imaginary line separating one basin from another, but it's a higher elevation, usually, what we would call it. But here in Arkansas, so I've got Arkansas popped up there again. I don't know how well you can see that, but you should have a copy of the map for yourself. But Crowley's Ridge right here, one of those other little provinces, a small one there in sort of the northeast part of Arkansas, Crowley's Ridge. So this is a natural divide that actually used to separate the Mississippi River and the Ohio rivers. And so, kind of during the last glacial period that we had, Crowley's Ridge separated the drainage basins of the Mississippi River and the Ohio rivers right here in Arkansas, and it is known as a divide. Now, what built up Crowley's Ridge, so back in the glaciation, the last glaciation period we had, the glaciers never reached down here into Arkansas, but further up, all that material that the glacier eroded and turned to almost like a rock flour, they call it, very fine grained sediment, got windblown, picked up by the wind, and was deposited in what we call now Crowley's Ridge, this loess deposit. And we'll talk more about that when we talk about our glaciers. But it built up sort of a natural high elevation that really separated those two rivers, the Mississippi and the Ohio River. And it was a natural kind of a divide. Closer to home, I mentioned the Bayou Bartholomew. Let me see if I can find another picture here. And the Saline River. Let's see if I can find that. Yes, this picture here. So a higher elevation, right, is kind of a divide, drainage basins kind of there. And so Highway 425, yeah, runs right down. That's like where everything is in Monticello, is on Highway 425. Running along there, making its way to Star City, Pine Bluff. If you take that route anymore to Pine Bluff or Star City, Highway 425 runs right through there. That was a natural divide, and it actually divided the Saline River and Bayou Bartholomew that we mentioned earlier. So here we go. There's Bartholomew, and there's the Saline River, right? And they go on up towards Pine Bluff. And 425, yeah, is going to run right on through there. And so Highway 425 is a natural divide that separates the Bayou Bartholomew and the Saline rivers. So there's Saline and Bayou Bartholomew, okay, for your spelling in there. So that's closer to home. We kind of have a little divide, right? Okay, closer to home here. A good example of a divide is Highway 425. Yeah, and then Crowley's Ridge. Maybe I'll write Crowley's Ridge up on the board. Just in case you can't read that very well on your map. So kind of during the last glacial period, this got built up from all that fine rock flour, glaciated, eroded material, windblown, and built up this divide here that separated the Mississippi River. Actually went on the west side of Crowley's Ridge, and the Ohio River on the east side of that ridge, and then they met up before. Of course, that has changed now. That is no longer the case where those two meet up. Now those two meet up up there in Cairo, Illinois. That's where the Ohio River meets the Mississippi River. So rivers change course over time. They certainly do. Okay. Oh, well, they got a little picture there of the drainage basin. Listen, it's nicely color coded as mine was there. But yeah, all of that region is draining into that huge drainage basin we call the Mississippi River drainage basin, right? And so a natural divide would be high elevation. So here we have the Appalachian Mountains off into the east. That's a high elevation, right? That's a divide. And of course off over here you've got your Rocky Mountains, again another natural kind of land divide because of the higher elevations there. It separates your drainage basin. I don't know that this is in your 8th edition book, but it's in our PowerPoints here. Drainage patterns that they talk about here. We've got several. Just kind of what the pattern looks like on how the rivers or the streams are draining. And so dendritic, and they'll have some pictures of them. Dendritic is coming from a term, dendro, meaning tree-like, so resembling a tree. Dendro comes from tree. So dendritic pattern it might have. Looks like a tree, dendritic. Radial, so it kind of starts at a central location and radiates out, maybe like spokes on a wheel sort of thing. Rectangular, so it's kind of going through some erosional resistant, kind of going along fault lines or joints in little fractured joints in the rock bodies, and it makes sort of a rectangular pattern or a trellis. So maybe it resembles a viney kind of trellis look to it, but they're giving us kind of some patterns to the drainage pattern of the rivers. Okay. Yeah, so here was the dendritic one. Kind of looks like the branches on a tree. Radial, so here we got a volcano, and then all of those little streams are going to make their way from that central point outward, almost like spokes of a wheel. Radial, they call that. Rectangular, so it's kind of just moving along the joints and the fractures in the bedrock, along little patterns where there were breaks in the rock. Kind of looks rectangular to it. Or trellis, so you can get little valleys that cut in the less resistant rock, okay? And then you get ridges where you have resistant rock that doesn't want to erode easily. And so it creates sort of this little trellis, little ridge, a little valley, a little ridge, and a little valley. Different patterns that they're talking about here for our drainage patterns there. So that's kind of our talk about the work of the streams, the running water of the streams, and the various types of landforms you can get. You can, of course, get the erosional landforms, and you can get the depositional landforms. So sort of that narrow valley, the downward cutting valleys where you're going to see the rapids, that very turbulent, choppy water, and the waterfalls in a narrow stream valley, versus we looked at a lot of the wide stream valleys, those floodplains, and all those numerous terms that we were using for those, the meanders, the cut banks and point bars, right? The Yazoo tributaries, the back swamps, the cutoffs, the oxbow lakes, right? So all of those terms from sculpting of the land from running water in our streams. Okay. Well, next we want to look at the water beneath the surface. And so this, again, as we mentioned at the beginning, the largest freshwater reservoir for humans is groundwater. Remember, it really only amounted to about 2/3 of 1%, 0.6% of all, our fresh water, all the water on the planet, that is our largest reservoir of fresh water available for human consumption, right? We can't use the ocean water. We can't drink that because it's got salts, various salts in it. It would make us very sick to drink that. So really, all we have is this groundwater that becomes very, very precious resource for us. So we want to look at the geological rules of even water. Yes, it does move, of course, downhill by the flow of gravity, that force of gravity. And it can be an erosional agent as well. So it can dissolve the materials by that groundwater, and it can create some erosional features. One, and we'll talk more about them, sinkholes. So it's actually eroding and dissolving away material beneath the Earth's surface, creating these little cavities. And eventually, if it becomes, so unstable, you can get a sinkhole out of that. The material will just fall right down into what then we would call a sinkhole or cavern. So the little excavated out kind of pockets where it dissolved out all that material because of the groundwater that was under there doing the dissolving. So it can be a very strong erosional agent. And they say that it is an equalizer of stream flow. So in periods of drought, let's say, periods when we don't get a lot of rainfall, what is sustaining our rivers is actually coming from the groundwater. Okay, so that sustains our rivers during even times of drought. When we're not getting replenished by rainfall. It's actually staying at a decent level because of the groundwater. So it's very much an equalizer of stream flow. Okay. And of course, yes, everything's going to move downhill according to gravity on this. And so dissolving, they call that solutioning, meaning it's dissolving in to create a solution. So they call that solutioning. That's a primary method of erosion of groundwater because it's not really flowing very rapidly like our stream flow is. So the velocity is not high, but solutioning, it will dissolve material very readily. Okay, so that's its main method of erosion. Okay, so distribution and movement of groundwater. Got some zones that we talk about, a belt of moisture kind of thing. So we've got pore spaces. I've got a little demo here that will hopefully represent it. So we do have materials that, rock material, if you think of maybe a sandstone, for example, little sand-sized sediments, there's little pore space in between. So these little styrofoam balls here are representing sediment, and there are little pore spaces between the sediment. Well, that can fill up with, of course, my groundwater here, and I'm probably going to have to try to keep that pushed down. But yeah, so it can seep down into it and fill up all that little pore space. Okay, it looks like those are going to float as I do this. Okay, push these down. Okay, so here we go. So all that water's filling in the pore space in there, but up here, up towards the top, you can still see that there's air in those pore spaces. And so they call that zone of aeration, okay, that unsaturated zone. And that's mainly filled with air, okay, that zone of, they say, aeration. Okay, but that zone of saturation, okay, are where all those pore spaces are filled in by the water. Okay, so water within the pores is called groundwater. So down in there, there's groundwater. So even here in Monticello, right, the sediment that we have right, gets filled in. Those pore spaces get filled in with water, and that is known as groundwater. We actually have a really nice aquifer, a water carrier, we call that, of groundwater here in Arkansas. Okay, so yeah, we got water in the pore fillings of the sediment in there. So yes, you've got your zone above, sort of what we call a water table, aeration, and then the zone below where it's saturated with water, okay, the zone of saturation, okay. Water table is the upper limit, okay, of the zone of saturation. So if I had my little, I could get it pushed down there, that would be like the water table right there. That's that upper limit of the zone of saturation, right? This would be the zone of aeration. Just has air in it. So some terminology for you to get under your belt there with that. Okay, so they've got a few pictures to help us with that. Okay, so we've got the zone of saturation in blue down here. So it's kind of showing you here that those little sediment pore spaces in between the sediment is saturated with water. Okay, and so that's the zone of saturation. Okay, up here, zone of aeration. So they've kind of magnified that picture there. We got air in those pore spaces, so no water. So zone of aeration. And along that line then, upper limit of the zone of saturation is the water table, they call that. Anytime you get the water table to intersect the Earth's surface, right, you can get just a natural spring that comes from the Earth's surface, right? A natural flow of water or groundwater known as a spring. So anytime the Earth's surface actually intersects the water table, you just get a natural flow. We call it a spring coming from the ground, from that groundwater. Okay. And they talk about some other things. So an aquifer, okay, is where it's like a water carrier. So along those pore spaces, water is flowing and moving. It actually is moving through there. That's an aquifer, okay. An aquitard, okay, as they're talking about here, is an impermeable layer. So you have different types of bedrock. Something like a shale layer, a very, very fine-grained material. There is pore space there, but a very, very small pore space. But those pore spaces aren't connected very well, so the water doesn't want to flow through it, so they call it an impermeable layer. That would act as an aquitard. It would resist the flow of water. Be an impermeable layer, we would say, in there. So they've kind of got an aquitard that they talk about in that picture there. So a few terms there for us to get under our belts, and a couple more here. So last time when we were talking about our stream flow, we had two C words, right? We had capacity and competence. Well, in talking about our groundwater here, the movement of the groundwater, we have two P words this time. First one is porosity, okay? The percentage of pore spaces, those little void spaces in a rock is the porosity of your rock. And of course, it's going to determine how much groundwater can be stored in those pore spaces. So that sort of the percent of void space in your sediment or in your rock is known as porosity. Okay, that's one P word. And then I've already kind of mentioned the other one, permeability. So the ability to flow through or transmit the water through the connected pore spaces is permeability. So how well does it flow through and transmit the water through? An impermeable layer as I mentioned before, something like a shale type of a rock, sedimentary rock, impermeable layer of material called an aquitard, but a nice permeable layer. Okay, we call that an aquifer, right? So that is what we use for our groundwater, like a water carrier, an aquifer. Okay, groundwater flows through it. Earth material that acts like a medium through which groundwater can flow is known as an aquifer. Okay, and yes, definitely, Arkansas has, or well, Monticello included in that, has an aquifer. I'm trying to think. I think I do have a picture of the aquifers. Yeah, here. That we have here in Arkansas. The Sparta is the one that, of course, Monticello uses. Drew County uses that one, called the Sparta aquifer. Okay. There is another one. Let's see. It's not on this image here, but the Mississippi River alluvial aquifer is another one. But in our region, it's the Sparta Sands aquifer. That is the one that we draw our groundwater from. Okay, what we use here. Okay. And so the recharging of the aquifers is very important, and actually a beneficial side effect of flooding is recharging of your aquifers. We always think of flooding as being bad, but floods actually will recharge your aquifers. Okay, so that is sort of a beneficial side effect of flooding, is recharging of your aquifers. But a problem with some of our aquifers is that we are pulling the water from the ground faster than it is getting recharged. And that actually can cause quite a few problems with that. And that's why we do think of our groundwater as being a precious resource. So yeah, there can be some, adverse effects. It's not just this unlimited supply. It does have to be recharged, right? So floods can actually be beneficial. We can think of those as being beneficial sometimes. So hot springs. So thinking about Arkansas and the hot springs area, we do have some hot springs. Here we're talking about hot springs. The water is 6 to 9 degrees warmer than the mean air temperature of the local region. Now, here they say that they're heated by the cooling off of igneous rocks. And so if you've been in the geology course, you should know that igneous rocks come from the cooling off of magma, molten earth material beneath the Earth's surface. And as that cools off, of course, it creates igneous rocks. Well, the hot springs here in Arkansas are not due to the cooling off of magma. Let's see, do I have that anywhere? I'm trying to think. Maybe I don't. Oh, here I have something. The hot springs that we have here in Arkansas are being warmed by what we call, and I've written it down here, so maybe you can write it down, geothermal gradient. So as you go down towards the interior of the earth, there's actually a warming as you're getting closer and closer right to the core. We're not going that deep, but as we go inward within the earth, yeah, it gets warmer as you go down in the earth. Well, in the hot springs area, okay, water, they're saying 4,000 years ago, rain has trickled in through all the cracks and crevices and made its way down, right, in through the bedrock, and have become warmed through just that geothermal gradient, that natural warming tendency as you go deeper into the layers. And then that water finds a nice little fracture here, a little fault line. It finds a nice fracture, and up it goes and comes out naturally as the spring water. So in the hot springs area, those waters are warmed by the geothermal gradient, not by the cooling off of igneous rocks. We do not have igneous rocks, any active igneous rocks cooling off here in Arkansas. So our hot springs are again warmed by the geothermal mountains, or I'm sorry, gradient. And they are and the hot springs is located in the geographic province of the Ouachita Mountains. And so that region is very structurally deformed to where you do have a lot of cracks and crevices for that water to seep down deep into. But again, that is in the Ouachita Mountains area, so the hot springs in the Ouachita Mountains of Arkansas are heated by the geothermal gradient. That's big long words there. But that's how our hot springs are heated, not by the igneous activity as noted in your PowerPoint there. Okay, geothermal gradient for ours. Okay. So yeah, that's a nice place to visit, and they're actually very, very warm, coming straight out from the ground. Okay. And geysers, okay, another thing that can happen from the heating of that water beneath the surface is what we call geysers. These are intermittent hot springs, something that the water will kind of heat up enough, turn to steam, and then erupt, okay? And so we think of Old Faithful Geyser in Yellowstone National Park. I mean, it goes off real regular. But yeah, so geysers are another sort of natural release of that groundwater, and it's been heated. Okay, and this is because of the cooling of igneous kind of rocks out in that area there. So, and it can quite be an explosive force here. About every 90 minutes, right? The Old Faithful Geyser will erupt with all that hot water ejecting. Very hot water, explosive kind of ejection there. So that's in Yellowstone National Park there. Geysers, and they're thermal springs, yeah. And they're ejecting hot water very forcefully, okay. And so the great majority of the hot springs and geysers in the United States are going to be found out towards the west, okay, out in that region. Because that's kind of the region that we have a lot of that volcanic kind of activity, the igneous activity going on that would warm the waters like that. But we're kind of special here in Arkansas, in the Ouachita area, because of the hot springs that we have from the geothermal gradient though. But in the United States, the majority of your hot springs and your geysers are going to be found out in the west of the United States. Okay, let's see here. So we try to get at our water, our groundwater, because that's the resource that we can use, right? It's our largest resource of fresh water. So we, of course, will put wells in there to draw out the water from our groundwater. We can end up causing some problems, like I mentioned. Pumping at a faster rate than what your aquifer is getting recharged, okay, can cause a down draw or a lowering of the water table, okay? And so some wells, if you're drilling those to the particular water table and you're doing good for a while, but then that water table lowers, you can end up leaving your well high and dry kind of thing. So what can happen when you're rapidly pumping that water and it's not getting recharged? You can form what we call a cone of depression. I'm wondering if I had an image of that somewhere. Oh yes, I did, right in through here. They may have a picture of it as well. But we can end up getting a problem there, you know, so water that gets drawn too rapidly. You know, here we have a well, it's doing okay, not pumping too rapidly, but right here, this one, really drawing too rapidly, and it forms sort of this, what they call a cone of depression. Let me see if I brought my thing. So here we have like a well, it's almost like a little funnel. And there's my well, and it's drawing, and it creates this cone of depression. So you're really pumping way too fast, and that groundwater will create that cone of depression shape to it, they say. And here in Arkansas, we can actually have a problem where if you do that and you're pumping way too fast, you can actually get some salt water. It's called a saltwater intrusion that can happen. With our Sparta sands here in well, Monticello, Drew County, that we use the Sparta Sands aquifer, those sands, this region, where's my Arkansas map? This region, see how it's called the Gulf Coastal Plain province? That is stemming from when, we're talking millions of years ago, when Arkansas, the southern part of Arkansas, was more like a Gulf Coastal Plain, where the Gulf of Mexico is now, down there by Louisiana. It was like that here in Arkansas. And so we had sort of a beachy ocean kind of a scene where all that salt water has been buried then in with the sands that we have here, the sands and the gravels that we have. And so it was more like a beachy scene. And so if you go deep enough with your water, you can actually start to get some of that salt that was left behind from millions of years ago when the ocean actually covered this region. So a saltwater intrusion is definitely a problem that you can get from this. And when you also draw down so rapidly like that, you change your pore space. You will change up your pore space. Draw something here. You reduce your pore space when you do that. So say here we've got, you know, all of our little sediments, nice, like that. You got your pore space here. Right, well, when you draw down like that, you actually create some compression happening, right, to where you decrease pore space. And once you lose that pore space, you don't get it back. And so that can cause subsidence of the land from that. So these are some problems you can get from really over pumping and drawing down your wells, this cone of depression here on your water table. So that can create a lot of problems. So yeah, so this is showing you a cone of depression. Right, and so before that all happened, this well here was doing fine. But when his neighbor, and he must have had a lot of money and was able to pay for a well that went much deeper, right? And so he drew down the water table and left this guy here and that guy there high and dry. So those wells dried up, and look at him, he's just really irrigating his crops with no concern for anybody else kind of thing. And created that cone of depression. That's a problem we can get with our aquifers. Okay. An artesian well, so the water in the well rises higher than the initial groundwater level, that water table. It's kind of like a pressure level. And so these will just sort of natural pipelines bring the water straight up. You don't even have to pump it, right? So if you get to that pressure surface and you build your well beneath that pressure surface, that water is going to go straight up. You don't even have to pump it. So we like our artesian wells, they call it. They act as natural pipelines, moving the water really from remote areas and can recharge great distances from their, their discharge point. So we like those artesian types of wells. But again, it has to do with where that pressure surface is. So right along here, you might not be able to see it too well, but there's a little pressure surface right along through there. We've got one well that's being dug right into here, and you're going to have to, the water will come up to that pressure surface on its own. You'll have to probably pump it from there to there. Not too big a deal, it doesn't look like that's too far. This one, because your pressure surface is up here, that well will flow all the way up to the top because it's beneath the pressure surface. So it's going to want to rise automatically. That's sort of a free-flowing, what we call an artesian well, free-flowing artesian well, they say. And we definitely try to make some artificial varieties of an artesian well, and you'll see that with our water towers. And so they're getting the water up into the water tower, which is really high up. Well, that ends up making that your pressure surface. And so all the homes down below your water towers are below the pressure surface. And so the water, when you turn on the faucet, will automatically come right out of your pipes, right? You don't have to do any pumping or anything. It will naturally want to flow right out of your pipes because your homes are located beneath the pressure surface. It's like an artesian well type of a flow situation, so an artificial. We like to make our water towers really high above the cities so that the water would come into the homes just naturally, okay? You don't have to pump it into your pipes kind of thing. So environmental problems that we can encounter with groundwater. So we do want to treat it as a sort of a natural, just non-renewable kind of a resource because it is so precious and it's limited, right, into our region. So treat it as a non-renewable resource. So what we did here in Monticello several years back, 1990s in that region, if I can find that one, to kind of, preserve kind of our groundwater resource, because we knew a lot of the farmland areas were really pumping on the Sparta Sands aquifer, and we didn't want the problems with the saltwater intrusion that can happen, is we created Lake Monticello as sort of a reservoir, a backup reservoir for our drinking supply, our water drinking supply. In 1995 was when they built Lake Monticello, and it really was built to ensure a source of drinking water for us because we're concerned about the Sparta Sands aquifer. So I don't know if you've heard lately that they have drained, or in the process of pretty much draining Lake Monticello, and the reason is they need to work on the levee system. The dam and the levees were not built properly, so that's one of the reasons, and I do believe some of the fish were just like eating up all of the grass and stuff, and so they're going to have to replant and rebuild, but they're planning to rebuild that and refill it, but right now they've been in the process of draining it so they can work on the levees. But this has been since 1995 is when everybody voted on it, a little tax increase because we wanted to ensure a supply of drinking water, a backup kind of resource, because we knew how precious our Sparta Sands aquifer is to us. And so these are some of the problems that you can get with the groundwater. So we do want to treat it like it is a non-renewable resource. If you remember the introductory chapter, the non-renewable ones. You're thinking, it's water, we got water, but not fresh water, right? So that groundwater is so, so important. But so another one, the land subsidence. It causes those withdrawals, right? So you're losing that pore space and the land will subside you don't get that pore space back when you overdraw on your aquifers. And contamination. So something that can happen, like I mentioned here in Arkansas, is especially southeast Arkansas region to the Sparta Sands aquifer, is a saltwater intrusion. We say, where did my little image go for that? The salt water that gets up in there. Yeah, there it is. Right, so that saltwater intrusion, if you're tapping into the salt water there, that'll kill your plants, right? It's not good for us to drink, but you don't want to be spraying that on your crops either, that salt water. So we call that a saltwater intrusion, right? If you draw down too rapidly on there. So that's contamination sort of thing can happen as well. So these are some problems we get with our groundwater. Okay, and earlier we mentioned some of that work of groundwater. So it is in motion. It might be much slower than our streams flow, but it is in motion, ultimately working its way back to the ocean, right? In our water cycle, our hydrologic cycle. So the work of it, and remember, solutioning, meaning dissolving of sediment materials, is how groundwater does most of its erosional work. So groundwater, often mildly acidic, and so acids can dissolve quite readily. It contains sort of weak, what we would say, carbonic acid. So as rain is coming through the atmosphere, and I know we'll talk about the atmosphere a little later, it's dissolving carbon dioxide. And as it dissolves the carbon dioxide, it creates what we call carbonic acid, a weak carbonic acid. H2CO3 is the chemical formula of that. And that will work on the bedrock of what we call limestone. Limestone, for those of you who've taken geology, know that the mineral in limestone is calcite. It's calcium carbonate. Acids are going to dissolve that for sure. So it dissolves the calcite that's in the limestone, and it will solution it. It will dissolve it and create little caverns and pockets right in there. So some of the features of the work of groundwater is a cavern formed by dissolving the rock beneath Earth's surface. Okay. Of course, that gets formed in the zone of saturation, so all the pore spaces that are filled with the water, the zone of saturation. And it does work on that limestone. It will definitely be working on that. And we do have caverns, northern Arkansas, something like a cave. Yeah, think of the northwest Arkansas. That's where you're going to see a lot of your caves in that region. Because of the groundwater and it's dissolving the limestone bedrock that we have up there in that location. So yeah, you can get, and I mentioned earlier, the sinkholes and the caves or the caverns. So here's a little picture. The bedrock is that limestone, very susceptible to any acidic type of water. So the groundwater being acidic, yeah, it is going to solution or dissolve out, right, little regions of that limestone. Of course, in that zone of saturation, the pore spaces are filled with that kind of acidic water, and you can get, you know, some instability and actually sink down in the sinkholes. Okay, so once that solutioning has occurred and created the little cavern, the cave in there, you can get some features that will form, and I brought some samples of it, but they end up water still kind of dripping through kind of the ceiling of the cavern, the cavity. Your water table has lowered, right? So now you're in the zone of aeration, and it kind of drips little by little and drop by drop and builds up these structures, okay? So you can get calcite being deposited as dripping water, then the water evaporates and leaves behind these calcite deposits, these mineral deposits, and they can be quite beautiful. I have one here. The names of these, if it's dripping and forming from the ceiling, okay, it's called a stalactite, okay, hanging from the ceiling of your cave. Well, that can also drip down to the ground and form kind of a mound coming up from the bottom of your cave, and that's called a stalagmite. So I've got some here, we call it travertine because of the limestone, but you can see just that layer. This is a slice through one of these, and I don't know what orientation it was taken out of the cave, so it's either a stalactite or a stalagmite. I can't be sure on that, but layer after layer after layer that you can see here over a lot of time there, and the water evaporates off and leaves behind that mineral calcite deposit, creating these beautiful forms here we call travertine, right? Okay. And here's kind of a cross section through, but we can kind of see, come and focus it all for us, just how drip by drip, drop by drop, and layer by layer it added to this. Beautiful. So there's some travertine. And I have these little soda straws, sometimes they call them, or dripstone, they call that. So this looks like a little straw, but layer by layer, yes, that would form. So I don't know if you've been to visit a cave before, but they will actually tell you not to touch anything because that will disrupt the layering effect in there, because the grease, the oils on our hands will prevent that material from sticking on there and creating another layer. So you're essentially, disrupting the beautiful structures from forming. So yeah, it will create sort of the dripstone, they call that, right? But yeah, a stalactite coming from the ceiling. I might have had a diagram for that. And a stalagmite from the bottom. So yeah, this is known as karst topography. I think your PowerPoint will say that here in a minute. But the stalactites are dripping from the ceiling, right, the roof, layer by layer. And some of that, yeah, will end up being on the cave floor, and that's a stalagmite. And eventually these can actually grow together and create these gorgeous columns, right? They call those columns. So this is known as karst topography, where you've had groundwater and pretty much it was a limestone that solutioned out, and then you get a little dripping. So these are some of the karst type topography, shape of the land, right? Topography and karst topography at that. Okay. Now you're going to see that, and I went ahead, made a little extra thing here so you could make a note of that. We're mainly going to see karst topography in the northwest part of Arkansas. Think of the Ozark Mountain region is where you're going to see where we have all that limestone. And so again, millions of years ago, this region was under the ocean. Okay, so little ocean creatures, okay, were living and living their lives, and then they died, and their little shells, which were made of calcium carbonate, the calcite mineral, rained down to the bottom of the ocean floor, which now is, part of the Ozark Mountain region. So there's a lot of limestone in the bedrock in that region, and the groundwater will dissolve that out, right? And so that's why we see a lot of the karst topography in northwest Arkansas, in the Ozark Mountain region. Okay, again, millions of years ago in the making for the bedrock in there. Oh, and this is just showing, some bats that you find in the caves, a cute little waterfall coming out of that cave through there. And this is a a cave fish, right? So they don't have the eyes. They don't need the eyesight because it's dark in there. So that's kind of an interesting creature that forms, a couple of the creatures that live in there. So think of northwest Arkansas, here in Arkansas, for caves, beautiful caves, Blanchard Springs, gorgeous place to visit. And here is a nice one where you can actually see some of the stalactites and the stalagmites that have combined to create a column, right? So beautiful topography to explore. Is your karst topography, your caves. So these are some forms from groundwater, the work of groundwater. And here they're just showing again, seeing how that groundwater, before the water table was up here and it pretty much dissolved out, little pockets of that limestone, and then the water table lowered. And so you've got a little cavern in there, fun places to go explore your caves, right? And so sometimes you can get springs coming right on out as well, and sinkholes. So sinkholes is another thing you can get. It just, you got the little caverns there. It's very unstable, and eventually that can collapse, and we do call those sinkholes in there. So yeah, they're circular depressions caused by the collapse of the roof of a cavern is a sinkhole. These are very common in the Orlando, Florida area. Yeah, there's an image, our last picture in here, of that being just houses like engulfed with these sinkholes. So karst topography, as mentioned in another document there, is formed by the dissolving of the rock at or near the Earth's surface, right? So work of groundwater in there. And again, caves, for one, things that are very common in karst topography, caverns and caves, and those sinkholes. So surface depressions, right? There's a little cavity under there, and the weight of that material above it becomes too heavy over time. And so sinkholes formed by the dissolving of the bedrock beneath, and then the cavern ends up collapsing. So you'll find that too. We're talking about Florida here. Areas that lack good surface drainage, right? So you've got regions that make that unstable under there, and you can get some sinkholes out of this. And so let's look at that picture here. This is like our last picture of our PowerPoints, but this is showing that house right there. That is a sinkhole, a circular depression caused by the collapsing of a cavern right from beneath there. That house got engulfed, and you notice the neighbors next door, right here. They've got a moving van. They are moving out because they know that they're probably next for their home next door here. So sinkholes are very common in Florida. So maybe make yourself a note. They're caused by the collapse of a roof of a cavern, and they are very common in the Orlando, Florida area. So make a special note of that in your notes that you're taking, hopefully. So this is chapter 3, the end of chapter 3, the sculpting of the land by running water, right? And even though groundwater, you don't think of it as running, groundwater does move. It's just much slower than our streams. So that concludes this chapter. We'll get to looking a little closer at glacial ice, because glacial ice does a lot of work as well, a tremendous amount of erosional work, and our deserts as well. So that's the information that will be in chapter 4. So I will get back with you on that one. So bye for now. Thank you.